Okay, welcome back everyone to Tuesday, May 11th. So what we're going to do today is basically introduce general curvilinear motion, which is just motion of a particle that's no longer on a straight line. And we'll describe that motion using rectangular components, which is Cartesian coordinates. And then we'll finish off and see if we can get through at least the beginning of the motion of a projectile, which is application of curvilinear motion. All right, good. So in general curvilinear motion, just like we did with rectilinear motion, we have to describe position, velocity, acceleration, and all those fun things. So now instead of using just S, which was our path, we have to consider some direction as well, and that's where we introduce our position vector R. So let's assume we have a particle. The particle is moving along a path S. Let's say some reference point here. So the S coordinate is always the coordinate that follows the path. We'll just call this blue line the path of the particle. And it's the S coordinate. And for curvilinear motion, we will typically describe the position of the particle by the position vector, and that's always with respect to some origin. So if we have some origin over here, call that the origin. Our position vector is just the vector that's pointing from the origin to our particle at some point in time, and that is a vector quantity. So curvilinear motion just means a particle that's moving along a curved path. And we'll always use vectors to describe this because the motion is in multiple dimensions, 2 or 3. And then we always have to distinguish between position vector R and the actual path function S, or S is just the direction or the dimension that represents the path. So position we'll define as the position of a particle at any instant in time. We'll call our vector R. So position at any instant time we'll call R, and that vector is also some function of time, and it has both a magnitude and a direction that will vary with time. So the magnitude of R we'll call, just write it as R, our magnitude, our absolute value of that vector, and it will have a direction. Issue with this pencil. And these will vary with time. So for example, we could show maybe the particle has moved some new position, and we have a new position vector. Call this R. The change in position, which we call our displacement, do this in green, would be the vector that is connecting two positions. So we'll call this R. All right, that's cool. So delta R is the change in position or our displacement. So delta R is also a vector, and this is our displacement or our change in position. And then lastly, we have our delta S, which is our along that path line. Do it this way. Delta S, and this is our change in position along the path. So we can also write, just for our change of position or displacement, delta R the vector quantity is just equal to r prime minus the vector r. So position is pretty straightforward. A bit straightforward, or pretty straightforward. We talked about in linear motion that the velocity was just the rate of change of the position of the particle with respect to time. And that's the exact same here. So if we draw our particle again, it's moving along some path. We have our origin, we have our position vector r. Try and draw that a bit better. Position vector r. And we said that our velocity at any instant in time is going to be tangent to the path of the particle at that instant. Our velocity vector, in this case, if our particle is moving to the left, our velocity vector would be tangent. And that would just be a lowercase v. And we have the same definition as before for average velocity, instant, and so on. So our average velocity our v average, and that is equal to our change in position r, delta r, divided by the time that has gone by. And then we take the instantaneous velocity by finding the limit as delta t approaches 0, and we get the derivative. So our instantaneous velocity v, sorry, I guess v average is also a vector. Our instantaneous velocity v is equal to the derivative dr dt. So we also defined something before, which was speed versus velocity. When we were talking one-dimensional motion, we didn't really care too much about the distinction between speed and velocity because velocity just could be positive or negative, and speed was just the absolute magnitude. Well, it's similar here, except speed now is a vector, or sorry, velocity is a vector. It has a magnitude and a direction. Speed is just the magnitude of that velocity. So speed is the magnitude, I should say absolute, of velocity. So we could also write speed, if we would just write the letter v not as a vector, this would represent the magnitude of our velocity. So we can write v is equal to magnitude of our velocity, and this is equal to s dt. So the derivative of the motion along the path with respect to time. And just to reiterate, the speed is not a vector. This is speed. This is velocity. So when we talk about the rectangular components, we'll talk about what that symbol actually means and how you calculate the absolute value or the magnitude of the vectors. Lastly, acceleration. So acceleration is a bit more involved than velocity, and we'll see why. So acceleration, again, represents the rate of change in the velocity of a particle. So if we were to draw a particle traveling on path s, we would have our particle at this point, would have a velocity here. And then it moves some distance away, and our velocity vector maybe changes this point here, and this is v. So we described something before called, or mentioned something called the hodograph. The hodograph, what that is think of our velocity vectors like our position vectors. So our position vectors are basically vectors pointing from an origin to our position in space of the particle. The hodograph is a vector representation of the velocities. If the velocity vectors were all pointing from the origin and pointing towards a magnitude or a value that represented their velocity. So if we took these two vectors here and we moved them to some origin, so we'll call this origin O, and we're just going to redraw these vectors. So the tail of the vector are all starting at the origin. The next velocity is at this point, and then the line connecting these, if we were to continue somewhere along here, would be our hodograph line. So all this is this vector is drawn here, this vector is drawn here, and if we plotted all of those vector lines as our particle moves along its path, we would end up with this red line, and that would be our hodograph. And we said that the vector of the acceleration is always perpendicular to that hodograph line. So our acceleration term, let's do this in blue, our acceleration term is always tangent to that hodograph, and that changes with time. So this is a little bit more abstract than what we might be used to. If we were to just draw a particle along its path, so here's our path S, here's our particle. If the velocity is moving along that path, so velocity is always tangent to that path, the acceleration is always going to be pointing inwards in the direction of curvature. So, for example, maybe it is here. And then we can also say acceleration is always tangent to the hodograph. So we've shown sort of what acceleration is graphically. How do we represent acceleration mathematically? So, but the exact same way as we did for acceleration or for velocity, we have an average acceleration and an instantaneous acceleration. We can define average acceleration as our acceleration vector with subscript avg, and that's equal to our change in velocity delta v over our change in time delta t. And then we have our instantaneous draw it down here. Our instantaneous acceleration a is equal to the time derivative dv dt, and since velocity is the time derivative dr dt, we can rewrite this as the second derivative of position d squared r dt squared. So this is the general equation for our acceleration.